When we perform ANOVA methods and we end up rejecting the hypothesis that the treatment, the factor level population means are all equal to one another, then we want to determine, well, which pairs of population means are actually unequal. And the way that we do that is through what are called multiple comparisons of pairs of means. So in other words, what we want to do is look at, let's say, two means. Let's say, to be general, mu sub I and mu sub I prime. This could be, let's say, mu sub 1 and mu sub 2. And what we do is we look at their difference. And how do we do that in terms of using inferences? We use confidence intervals. We use hypothesis tests. So for every single possible mean pair, we're going to perform these multiple comparisons of means. How many are there possible? Well, there are t choose 2, where t is the number of treatments, the number of factor levels. So in other words, t times t minus 1 divided by 2. So when t is equal to 4, like what we had with the Wheaties example, the number of multiple comparisons will be 4 times 4 minus 1 over 2, which is equal to 6. And here's just simply a listing out of all those different possible mean comparisons that we would want to do to determine which set of means are unequal to one another. Now let's suppose that each of these comparisons we use a level of alpha for our type 1 error rate, for, let's say, doing a hypothesis test. You can think of this equivalently in terms of confidence intervals too. And with our hypothesis test, so type 1 error rate is alpha. What's the probability that we make at least one type 1 error for all the multiple comparisons? Because we're not just doing one hypothesis test. In the Wheaties example, we would do 6 different hypothesis tests. Is the error that we do have at least one error equal to alpha? And the answer is no. So to help understand what the error rate would be, we need to be a little bit more precise in what we define as a type 1 error. Excuse me. And so what we're going to do is define something called an experiment-wise type 1 error rate. Some people will also refer to this as a family-wise type 1 error rate. We will denote that by alpha sub e, so e for experiment-wise. And what this represents is now the probability of making at least one type 1 error for all the multiple comparisons that you're going to make. Ideally, we would like to be able to control that, let's say at a low value, like 5%, 0.05. Now, the type of alpha that we have been talking about, which is for an individual hypothesis test, we're going to denote that as now alpha sub I to help differentiate it from alpha sub E. And there's a nice, interesting relationship between these two. So to see it, let's go back to what we learned early on in the semester when we were working with probabilities and probabilities associated with events. Let's say in a very simple situation we have two possible multiple comparisons that we want to make. Let's let A sub j be the event that a type 1 error unfortunately occurs for the jth comparison of the mean. So A1 is going to be the probability of a type 1 error for the first comparison. A sub 2 is the probability of a type 1 error for the second comparison. Okay, so well, what's the probability that we have at least one type 1 error? In other words, alpha sub e. Well, we can write it now in terms of these events. It's the probability of A1 union A2. So A1 could be true, A2 could be true, or both A1 and A2 could be true. And we've learned previously we could write out now this probability as the probability of A1 plus the probability of A2, and then we subtract out the probability that both occur, the intersection there. Now, of course, all probabilities are greater than or equal to 0. So the probability A1 intersect A2 is greater than or equal to 0. So because of that, let's say we just happen to ignore this part. that I'm scribbling out right there. That would mean then what we would have left over then will be larger than what it would have been before, because look at this, we were actually before subtracting out that positive value, or 0 or positive value. So because of that, then we can write now alpha sub e, which is the probability of at least one type 1 error, is less than or equal to the probability a type 1 error occurs for the first comparison plus the probability a type 1 error occurs for the second comparison. Okay. So if, well, what is that probability for a type 1 error for an individual comparison? Let's say it's alpha sub I. Then that means then that alpha sub e, probability of at least one type 1 error, is less than or equal to 2 times alpha 1. And one could extend this little algebra here that we're doing to, let's say, m possible multiple comparisons, and the probability of at least one type 1 error is less than or equal to alpha time less than or equal to m times alpha sub I. So in other words, alpha sub e is less than or equal to m times alpha sub I. So what that means then is the probability of at least one type 1 error could be as high as m times alpha sub I. So if m was 6, as what we had in the Wheaties example, and if, let's say, alpha sub I was 0.05 there, then that means alpha sub e could be as high as 0.3. Wow, that's pretty high. Could be. We don't know what it is, though. Okay? Well, to take this into account, then, that the experiment-wise type 1 error is not the same as each of the individual type 1 errors. Meaning it's not like 0.05 only. It's likely to be something larger. To take that into account, there have been many different multiple comparison inference procedures developed in a way to either state alpha sub e or, let's say, bound it, give it an upper bound of what it could actually be. So there's been many. In fact, there are actually whole courses taught at some universities devoted to just multiple comparisons. We're going to focus on 3 commonly used multiple comparison methods. The first one is called Fisher's Protected Least Significant Differences, or LSD method. It's unfortunate, LSD does not mean the illegal drug there. It's just a way to abbreviate least significant differences. The second method is going to be called the Bonferroni method. And the third method is going to be Tukey's Honest Significant Differences, or HSD method. If you find this stuff interesting, there's actually, as you might expect then, if there's whole courses on this subject, there are whole books on this subject. Here's one particular book that's often used by people. Okay, so let's talk about Fisher's Protected LSD. Well, to see this, let's go back to when we were finding a confidence interval for the difference of 2 population means. When we had our samples taken in an independent manner, here's what that confidence interval looked like. Unfortunately, I'm going to run out of room here. So I'm going to multiply it by S1 squared over N1 plus S2 squared over N2. Okay, this is what our confidence interval was. We're basically doing the same thing here, but with some minor adjustments. So now my sample means are denoted as, let's say, Y bar I dot. So that's the sample mean for the ith treatment or the ith factor level. And then Y bar sub I prime dot. So again, the I prime is just meant to say something other than just I. So I could be 1, I prime could be 2. So Y bar I prime dot. So it's a sample mean for the ith prime treatment level. We subtract off again a value from our t distribution. Notice where alpha sub I is, the individual test type 1 error rate. Divide by 2, just like what we do normally. And then for the degrees of freedom, now it's n, capital N minus T, where capital N represents the total sample size. T is the number of total treatments that we are dealing with. Then we take that times the square root of the mean square error. Remember how that kind of measures it's a measurement of variability, times the quantity, 1 over the sample size for treatment I plus 1 over the sample size for treatment I prime. That's our confidence interval. Again, look how similar this is to what we had up there. That's the lower bound of the interval. The upper bound ends up being the same, but now I put a plus there instead. So that's the confidence interval. To do the hypothesis test with, let's say, a test statistic, very similar to what we saw previously when we were doing hypothesis tests for just 2 means. We have the 2 sample means up here, and since we're checking are the population mean differences equal to 0 or not, we have a 0 there, so you could actually just remove it. Divided by the square root then of MSE times this quantity that represents the inverses of the sample sizes added together. We check it up against a critical value from the t distribution, same critical value or the same quantile that we use with the confidence interval. We could also use a p-value as well. So the probability that a random variable t is greater than what we observe t to be, we take 2 times, and we have an absolute value there as well. That will be our normal p-value. So that's how one could do the hypothesis test using the Fisher's protected LSD. There's another way to do this. I'm not going to ask you a question about it, but it leads to the reason why it's called Fisher's protected LSD. And that is, what we could do is look at the absolute value of the difference between the 2 sample means and compare it to what was on the right side of our confidence interval. And if this difference in the absolute value is greater than the quantity that was from our confidence interval, then we could say yes, indeed, the 2 population means are different. Okay. So where does this name protected, Fisher's protected LSD comes from? Fisher is named after a famous statistician. Protected comes about that we only ever perform this procedure, this multiple comparison procedure, if our hypothesis test for the quality of all means is rejected. So to some respect, we are protecting ourselves against making a possible error. I mean, you could still make it, but you should feel better about yourself by only doing this procedure if the overall hypothesis test of equality means across all treatments was rejected. The LSD comes from this part right here. So what we're doing is we're looking at what is the smallest possible value of the difference of the 2 means. What's the smallest possible value such that we will reject the hypothesis of equality of means? This is the smallest value. So the least significant difference. That's where that name comes from. Now, unfortunately, this protected LSD method does not give us a measure of the experimental wise error rate, though. It is still widely used, but it doesn't give us a measure of that. What one procedure does help us somewhat get a measure is this procedure called a Bonferroni multiple comparison. Okay, here's how it works. So remember, our alpha sub E, our probability that we make at least one type 1 error, is going to be less than or equal to m times alpha sub I. Okay? So what we could do then is take the Fisher's protected LSD procedure, wherever we saw an alpha sub I, how about we replace it with alpha sub E divided by M? So notice what happens then is, well, let's look at an example first. So let's say that we want alpha sub E to be 0.05 and M was equal to 2. Then simply what we would do, and perhaps I didn't say that necessarily correct there, excuse me. So what we would do is we take alpha sub I and we set that equal to 0.05 now divided by 2. Indeed, I think I did say that right before, excuse me. And so now we're in the Fisher's protected LSD procedure. Wherever we would have normally put 0.05, now we're going to put 0.025. Let's look at another example to help clear this up just in case. Let's say M is equal to 10. Okay, so we have 10 possible multiple comparisons to make. And so what we're going to do is that if we want our overall experimental error rate to be no more than, let's say, 0.05. Oops. I don't know why my computer's not working very well. If we want it to be no more than 0.05, what we can do is take this 0.05, divide it by 10, so we have 0.005, and we use that as alpha sub I. And it's all based upon, sorry, my computer is not working very well here. But if you remember what was there before, I had written that. And if you look at the notes, you could see that inequality. And because of that inequality there, that's why we can use this now 0.005. That's what we would use everywhere where we saw alpha I before in the Fisher's protected LSD procedure. So just for completeness then, here's what our confidence interval then would look like. Notice what we're doing here. We're taking this alpha sub E, we're going to divide it by M. But normally we would have alpha sub I divided by 2 there. So that's where that extra 2 comes into play. There's where this is our confidence interval. Here's when we were doing a hypothesis test. Here's where what would happen to our critical value. Now we take that alpha sub E divided by N. We put it where we saw alpha sub I before. So now the critical value is alpha sub E divided by 2 times M. In terms of the p-values, some people kind of think it's a little bit more complicated, but in the end it really isn't. What we can do is as follows. So I think you will agree with me, or you should agree with me, that we're going to have a smaller number here in the subscript for the t. So instead, if we were to draw out the t distribution, so instead of, let's say, being right here with the t distribution, since I have a smaller value in that subscript, now I might be way out there. So it's going to take more to reject HO than what we did before. So in terms of a p-value then, you would think it would take a smaller p-value then in order to reject HO than what we had before with the Fisher's protected LSD. And indeed, that's the case. Now what we can do is check our p-values that we would normally get from Fisher's protected LSD, and instead of comparing it to alpha sub I, we're going to compare it to alpha sub E divided by M instead. It all has to do with that inequality that we saw. Now, sometimes p-values will be automatically adjusted for you so that you don't need to take alpha sub E divided by M. And instead, these p-values will be adjusted in a way that now you can just simply compare to alpha sub E. This is what R does, so it's very important that you understand that aspect. And here's the simple p-value adjustment. Take your p-value that you normally get before, take it times M. So in other words, it's going to inflate what you would have had before to account for these multiple comparisons that are being made. Now, depending upon what the p-value is and depending upon what M is, you could have a result of that's greater than 1. And of course, a probability can't be greater than 1. So what's done then is we take the minimum of the p-value times m, that minimum of that and the value of 1. And then that's the actual p-value that will be reported. We'll see examples of that coming up shortly. Our third multiple comparison procedure is referred to as Tukey's HSD. Tukey's a famous statistician, so it was named after him. So this particular procedure uses a different probability distribution to help make our multiple comparisons. And basically, it's based upon this statistic here. Let me get my pen out again. Suppose you found the largest of your sample means corresponding to your treatments or your factor levels. And suppose also you found the largest sample mean, the smallest of the sample means corresponding to the treatment levels, the factor levels as well. And if we take that divided by the square root of MSC divided by n sub minus t, then we get this statistic that we see here. And this statistic is very similar to what we saw before, but now since we're saying, okay, this is the largest, this is the smallest, unfortunately the mathematics behind everything doesn't work out exactly the same. And in fact, this statistic here has a different probability distribution, which is called the Studentized range probability distribution. Note that basically we're kind of looking at a range of the means. That's where that name comes from. Studentized comes from, if you remember, students' T distribution. We're forming a similar type of statistics. So that's where the studentized part comes in. And it's just another probability distribution. It's not worth our time to go through, here's a picture of what the distribution is, here's how you can plot it and stuff like that, because this is the only time that we're ever actually going to use this, this probability distribution. And also there's not a convenient way to actually graph the probability distribution in R. But I will tell you is that there are functions such as P Tukey and Q Tukey that allows you to find probabilities and quantiles with the distribution, just like what we've done before with so many other functions, so many other probability distributions. Okay. Now, in order to use this procedure, here are some important items behind it. We can find confidence intervals in much the same way as we have done before. Now, instead of using a t-distribution, we use a quantile from this corresponding studentized range probability distribution. And we also make some changes here underneath the square root, a small change. Our test statistic, based upon what we saw above, here's our corresponding test statistic. Our p-value, we would find that in much the same way as we would normally as well. In this particular procedure, the experimental wise error rate is actually alpha sub e. And in case I didn't say this before, excuse me, with the Bonferroni procedure, the experimental wise error rate for Bonferroni ends up being less than or equal to alpha sub e. Okay, so with Tukey's HSD, exactly alpha sub e. And I guess I did put it right there. So comparisons of the multiple comparison procedures. How do we control the experimental wise error rate? LSD, there's none. Bonferroni, there's an upper bound. HSD, we have it set. Okay. Of course, all the above values are conditional, excuse me, on all the assumptions behind ANOVA being correct too. Now, typically, people think of the LSD as what's often referred to as a liberal statistical procedure. And the reason why that name is associated with it is because it ends up finding, let's say, perhaps more differences amongst the population means than actually truly exists. It can do that. The Bonferroni procedure is often referred to as a conservative procedure because it will sometimes find less differences amongst population means that truly exists. And so in many different statistical applications, you will often hear the words liberal and conservative. And it all is associated with something like this. How often does the error occur? Does it occur more often than what you would expect? A liberal procedure. Does it occur less often than what you would expect or what's stated? That's a conservative procedure. Okay. Now, before we actually get to an actual data example, let's talk about how we can actually concisely display the results of the m different hypothesis tests or m different confidence intervals that we're going to form to do these multiple comparisons. And the way that we concisely state these results is through kind of an interesting graphic. And here's how to construct the graphic. First of all, imagine, let's say you have treatments A through D, and they have corresponding sample means as I have shown there. This doesn't correspond to any example that we've seen before. It's just, I've made this up here. And so let's actually write out an ordering of the sample means based upon these, oops, yeah, I wanted that there, excuse me. Sometimes it's hard to write and talk at exactly the same time. So what we're going to do is write out these letters corresponding to an ordering of the sample means. So treatment A, factor level A, had a sample mean of 1. That was a small, so that letter came first. Treatment D had the next smallest sample mean, so that letter came second in how I'm writing everything out. Then, step 2, we place bars over the treatment letters when there is not sufficient evidence to show that their means, their population means, are different. So, for example, let's say we have this particular diagram as shown here. What this is telling me is this. Since A and D have a line over them, that says I was not able to reject that the means are equal to one another. So there's not sufficient evidence to indicate that the means for treatment A and treatment D, the population means, are different. Now for D, C, and B, notice there's a line on top of those. And similarly, when I did all those multiple comparisons amongst those corresponding population means, there wasn't enough evidence to say that those pairs of means were different. So C and B, there wasn't sufficient evidence. D and C, there wasn't sufficient evidence. D and B, there wasn't sufficient evidence to indicate difference amongst the population means. But notice, there is no line at all connecting A to C and A to B. So what that means is, yes, when we did a hypothesis test comparing the, let's say, mu A to mu B or C, we were able to reject HO. And so a convenient, a concise way to organize all 6 of these comparisons is to do a little graphic like this. You might be thinking, well, geez, there's only 6 comparisons that were made. Why do we even need to do a graph like this? I can look at the results. But imagine if you were in a situation where there were a lot more multiple comparisons. Then definitely a figure like this, a graphic like this, can be very helpful to make sense of everything concisely. Now, do note that some books, some people outside this course, instead of putting lines on top, they will put lines on the bottom of a list of the treatment letters or ways to denote the treatments. Okay, now finally we get to an actual numerical example. We're going to go back to the Wheaties case here, or Wheaties example. And remember, we found when we did the overall hypothesis test for equality of means for the 4 different design types, we ended up rejecting HO. So now what we want to do is find out which pairs of means for the design types are different from one another. And this will then potentially lead us to a strategy to, let's say, recommend to General Mills about, well, which of these design types would maximize the corresponding sales for Wheaties. Okay, so what we want to do is 6 different hypothesis tests corresponding to these hypotheses there. So we want to do, for example, when I is 1 and I prime is 2, we want to do this hypothesis test. when I is 1 and I prime is 3, we want to do this hypothesis test. And let's say we want to set an experimental wise error rate of 0.05. Ideally, this is what we would like to have. So what we've done in the past is that we've already got like an ANOVA table. We got some summary of the results. We put the results into an object called ma.fit, and this contained the results from the AOV function. We could also do this as well with the LM function too. Okay, so first of all, let me remove that. We can use the aggregate function, as we've done many times before, to find, let's say, the sample means for each treatment type. And so notice that treatment 2 has the smallest sample mean, then it's treatment 1, then it's treatment 3, and then it's treatment 4. And we'll use this ordering then when we do this little graphic. To do the multiple comparisons, we can use a function in R called Pairwise.t.test. Let me actually go over here and do that. So Pairwise.t.test. So we're essentially kind of doing t-tests for pairwise comparisons of the means. For the x argument, we put in what my y sub ij would be in my data set itself. It's the Wheaties, the response variable in Wheaties. G corresponds to, let's say, a grouping. In other words, the factor levels, the treatment types. And that was corresponding to design. Note that I do not need to actually use the function factor with it. And then how do I want to do an adjustment here so I can control the overall type 1 error rate, the experiment-wise type 1 error rate? That's what p.adjust.method means. So p-value adjust, and I'm going to put none there, meaning I'm going to use Fisher's LSD essentially, or that is what it means. And then I'm always going to do two-sided tests. So let's go ahead and do that. And so then what's produced then is a whole bunch of p-values. So let me go back to my Word document. So for the test of mu1 minus mu2 equals 0 versus mu1 minus mu2 does not equal 0, I find the 1 here, I find a 2 there. Here is my p-value. So p-value equal 0.4589. I can compare that to what I set my experimental wise error rate to be, 0.05, to make a judgment. Do I reject or don't reject? In this case, I would say don't reject HO. Now, even though I am comparing it to that 0.05, it doesn't mean that Fisher's LSD is actually controlling the overall type 1 error rate at 0.05. Well, what about then, let's say, comparing population 1, or I'm sorry, in this case, design type 1 to design type 3. Here's the p-value, 0.1646. So what that tells me is, again, there's not sufficient evidence to indicate a difference in the mean sales for design 1 versus design 3. But now look at if I compare 1 to design 4. Now I get a really small p-value. So what that does tell me is that, yes, indeed, there is sufficient evidence to indicate that design 4 and design 1, there is a difference in the actual corresponding population means. And you can look at the other p-values as well. So, for example, the 0.0194 there is comparing mu3 to mu4. So let me do some erasing here. So then, oops. Here's our corresponding graphic. So we order the means again. So remember, 2 was the smallest. And remember, for 1 and 2, we had a p-value that was greater than 0.05. So that's why we drew this line on top of it there. Well, what about 2 and 3? Well, let's look at 2 and 3. Well, take a look at that p-value. Well, it's below 0.05. So I don't want to see a line between 2 and 3. So in other words, I'm not going to continue to extend it in that direction there. I'm not going to do that. Okay? How about 2 and 4? Well, its p-value is small as well, so I wouldn't extend it out there too. Now, because we've ordered the means here, if I know that 2 and 3 is not going to have a line between it, I know 2 and 4 is also not going to have a line between it too, because its sample mean was higher. Okay. Now, we keep on going here. Let me do some erasing again. Let's compare 1 to 3. Here's my p-value. Notice that is greater than 0.05, so that's why I have this line up there. But 1 and 4, p-value is less than 0.05, so I do not extend the line any farther. Then with respect to 3 and 4, we see that we have a low p-value as well, so that's why you don't see a line between 3 and 4. But let's say that instead we use 0.01. What would happen? Okay. So in this particular situation, now I need a tougher, I have, let's say, a tougher criteria to meet in order to reject HO. And so let's compare 1 to 2 and 2 to 3. None of those p-values are less than 0.01, so that's why you see a line between 2, 1, and 3. I mean, you can even look at 1 and 3 as well. For 3 and 4, that p-value now is greater than 0.01, so that's why you see a line between 3 and 4. But all the other p-values are less than 0.01, so that's why you don't see a line connecting them. So for example, compare 2 to 4, that p-value is 0.0015, which is less than 0.01. So that's why there's no line between 2 and 4. What about using the Bonferroni procedure then? Exactly the same code as before. Now I have Bonferroni there instead. And what R does, it automatically adjusts the p-values to, let's see if I can get this both on the same screen here. Oops. Okay, let's see here. Can't quite do it. Let me actually copy and paste some of this stuff so that I can. Give me one moment, please. Okay, so on the bottom we have from Fisher's protected LSD. The top we have these Bonferroni corrected p-value or adjusted p-values, you could say. So let's take a look at, let's say, we'll compare 1 to 4. Okay, now remember there are 6 different comparisons. So if I find the minimum of 0.0294 times 6 with 1, I would get, oops, actually, I'm sorry. Excuse me, I wrote that wrong. I would get 0.00, oops. Okay, let me restate that. So without the correction, the p-value is 0.0049. That's from Fisher's protected LSD. If I take that 0.0049 times 6, I get 0.0294. So that's the relationship between these two different tables. And let me erase that now. I'm going to erase that, and then I'm going to remove what I got here from protected LSD. Okay. So now what I can do is I can look at these 0.05 and compare it to these p-values directly. And what I see is, for example, this p-value is less than 0.05, this p-value is less than 0.05 as well, but all the other p-values are greater than 0.05. And that's what's reflected in this diagram here. So for example, if we look at 2 and 1, that is a p-value of 1. In the end, that minimum kicked into play there, where the previous p-value from Fisher's protected LSD was such that if you take that times 6, you get something greater than 1. And so thus are set then that top possible value of the p-value to be 1. So between 1 and 3, p-value 0.9877. Between 2 and 3, it is 0.227. So that's why we have that line being extended. Now I go through some of the details of what I just went through here, where I actually go through the multiplication. Please see that. Make sure you understand that. Well, what about Tukey's HSD, though? Well, unfortunately, this particular function, the Pairwise T Test function, doesn't work with it, but there is a separate function called Tukey HSD. And you put the results that you save from the AOV function in it, which notice that is different from the pairwise.t.test function. You put your confidence level as well, let's say it's 0.95 in there, and this is what we get. We get a set of confidence intervals now rather than, well, we also get p-values. So we get p-values, here's the confidence intervals. So in this particular case, we're looking for p-values that are less than 0.05. So we have this one and this one. And that leads us into the exact same graphic that we saw before. So using 0.05 then as our experiment-wise type 1 error rate. What that says then for us is that design 1 and 2 are different from design 4. There's not sufficient evidence, though, to say that design 3 is going to give you more or less sales than design 4, though. And there's not sufficient evidence to indicate a difference between designs 1, 2, and 3. So because of that, then, and also because, so we want to know which of these mu sub i's is actually the greatest based upon information from our sample. Remember how the sample mean for design 4 was actually the highest. And because I can't say that design 3 has a different mean from design 1 and 2, that means I would go with design type number 4 as essentially the best of these design types in terms of maximizing my sales. Okay, so how else can we do some of these multiple comparisons? And so I want to show you this because while in this class, I try to stick with the packages that are in the default installation of R. But sometimes when there are other packages that have been developed that can actually produce better results, I do like to at least include those in a discussion. And in particular, here are two particular packages that are often used that are outside the default installation of R. This first one is, I guess you pronounce it Agricole, maybe. This is, again, a package that you're going to need to download yourself. And the way to use it is that there's a function called lsd.test, where the y argument corresponds to what you get from the AOV function. In this case was mod.fit. And then there's an argument that says TRT, that stands for treatment. And this is what you have to use to denote that you're talking about the design types with respect to the Wheaties example. In quotes, factor, parentheses, design, and parentheses. Well, why am I using that? Okay, let's look at the output that we got previously. Okay, so here's my AOV function. So notice how, remember I had to use the factor function with design to get this all to work. Notice how our labels in the output now factor, parentheses, design, and parentheses as essentially our way to note our factor levels, our treatment. So because of that then, I need to use that exact same name then for the TRT treatment argument of the lsd.test function. That's why. Then I set my alpha level. This is what you hope to be the experiment-wise error rate. Group equal false. The default is true. Basically, what will happen if you do true, and you can try that on your own, you're going to get something that's somewhat similar to these diagrams that we were talking about there. But it doesn't use lines at all. It just uses a different format that's less common. You're welcome to take a look at it but I think we can find that. I think it's instructional for us to be able to do these kind of diagrams on our own. Then P.ADJ stands for p-value adjustment. There's none, meaning that I wanted to use Fisher's protected LSD and just put a title to everything as well. So let me make sure to emphasize that you would not run this function unless you actually rejected the overall hypothesis of equality of means when you are using Fisher's protected LSD method. So even though it says none, well, still it's expected that you know what you're doing and that you wouldn't do this procedure unless you had originally rejected. Okay, so inside of then the object that I have saved, then we get some information. And the most important information then comes down here, where here we have comparisons. So for example, I want to compare the mean for treatment for design type 1 to design type 2. I want to compare the design type 3 to design type 4, and so on. Here's the mean difference. Here's the corresponding p-value that has been, in this case, we're not doing adjustment, so it has not been adjusted. Here's the corresponding confidence intervals as well. Now, if we were to do the Bonferroni procedure, we use exact same code, but now P.ADJ has an argument value of Bonferroni. Okay, we save the results, let's say in save.bon for the lack of a better name. Now these p-values have been adjusted, just like what we saw before. We also have the corresponding confidence intervals that include the adjustment too. Okay. This package does not allow you with this particular function to do the Tukey's HSD, but there is an HSD.test function that can be used instead, and it works in a very similar manner. Okay, lastly, for those who are, let's say, doing hardcore statistical analyses that maybe go beyond like using a completely randomized design, these people typically use a package called multcomp for multiple comparisons. And this package corresponds to what is taught in this multiple comparisons book that I mentioned towards the beginning of this set of notes. And I won't get into the details behind this particular package, but I at least wanted to bring it to your attention that if you do more complicated work, it's very useful to look into this more, especially if you take a course on experimental design. So this package is not automatically installed in R, so you have to download it, tell R you want to use it by using the library argument. Then you can use the GLHT function to do your comparisons. Notice how I have a Tukey there. And if you do a summary here, we get output very similar to what we've seen before. You are not responsible for this particular package to use it in our class. You are responsible, though, for the previous package. And sorry, I think I failed to say that. You are responsible for working with this package because it's a nice package to work with. Okay, so let me go back down here. One nice thing about this multcomp package is it actually gives you a plot of your confidence intervals, which can be a nice graphical tool to see what's going on as well. So notice here's 0, and you can see comparing design type 1 and 4, design type 2 and 4, notice the intervals do not contain 0. Okay, so then that ends then this particular section on multiple comparisons.